Hi everyone, this is Mr. Chew over here, and this is going to be the first of the revision lecture series that I will be doing for you. Today I'll be covering topic 2 and topic 3, and I'll be touching on the key ideas. I will not go through the whole topic, I'll go through the key things that you have to know. And I'll be going through some possible tricks that you have to be careful of, and hopefully this will help you prepare better for your exams. Okay, so let's start off with topic 2.1. Now topic 2.1 covers kinematics, and of course it will cover the use of the four equation: s equals to ut plus half at squared, s equals to u plus v divided by 2 times t, v equals to u plus at, and v squared equals to u squared plus 2as. Now the equations itself is not good enough, you have to know how to use them. Remember that when I went through with you in lessons, STUVA, usually you have to identify what is known, what is unknown in the question, and then usually in IB question you have one variable that you don't need to, that you're either not given or you don't even need to find. So say for example, if you know S, you know T, you know U, you want to find V, but you don't want anything with A. So it is always easier for you to find an equation that doesn't have the quantity you don't need. This is the equation. So always look out for the equation that doesn't have the quantity that you don't need. So it is easier. For whatever reason, psychological or cognitive reasons, it's easier to find the equation without the quantity that you don't need. Now, other than using this equation, knowing which quantity to use, which equation to use, you have to be very careful. I can't emphasize enough. You have to be very careful about the sign convention. So say for example, in this case, if I throw something up and I want to find the time it takes to go down, this is usually taken as the reference point, the 0 point. So if I take upwards to be positive, then the S will be negative because it's pointing down. The A will be negative, the U will be positive because it's pointing up. So you have to be very careful about the sign convention. Even for myself, up to now, I will still put a big fat arrow pointing where the positive sign is. Okay? So just repeat the two things I mentioned. Know which equation, know the method to identify the equation, and also the sign convention. Cool? Next one. Next thing I'd like you to know is this thing about the graphing. So xt graph, vt graph, at graph. You have to know that the gradient of each of them gives the one below. Whereas you have to be very mindful that this area over here gives you the change in velocity, area over here gives you the change in displacement. It is not the velocity, neither is it the displacement. It is the change in the velocity or the change in the displacement. So you have to be very careful because sometimes the initial velocity or initial displacement is not 0. It is actually some value. So you have to add the change to the initial value. Cool? So these are things that you have to be careful about for the linear motion. For projectile motion, it is actually quite similar to linear motion. I went through with you in class that if it is a projectile motion, you have to remember that the Vx is constant and then the Vy is under the influence of the gravity. So everything else is the same as a linear motion like this. This object would have exactly the same time as this object to reach the ground. And if you have to find the horizontal information about horizontal direction, you just have to take the time over here times the horizontal velocity. So most of the time, I would say 95% of the time, if you have to solve for the time of flight, you will use the vertical direction, 95%. Sometimes they may give you enough information for you to use the horizontal, but most of the time, time of flight, vertical. Okay? And the next part, which is 2.2 forces, I need you to know how to add forces. Now I'm going to go through two examples because those are the examples that you need to know. I'm not limiting to, but most of the time. So if you've got F1 and F2, whenever you want to add forces or vectors in general, make sure you align the vectors so that the tail meets the head. So this will give you your resultant. Alright? And the other situation, say for example, if I got F1 plus F2 equals to FR, but I only give you F1 and FR and ask you to find F2. So how do you go about this? So say this is FR. Now you have to transform this equation into a form that gives you F2. So it's FR plus negative F1. There's a reason why we put negative. Because you have to sum the negative of F1, which is this one. So this will be your F2. Alright? So let's summarize the two examples. If you're given F1 and F2 and find FR, it's very simple. Align the head to the tail and always from the very tail to the very head. The method is actually more or less the same for this one. Just that you have to align, if you want to find F2, given FR and F1, you have to flip F1 around like this. And then you sum using the same method. The head must meet the tail from the very tail to the very head. Cool. The next thing about forces is that you have to know this notion of, you have to know this concept of frictional force, where F is equals to, I have to emphasize this F max over here equals to mu n. It can be equals to mu s n or mu k n. First point, you have to know that this is normal contact force, not weight. Which means that if I have an object in a lift and it moves upwards, the normal contact force is actually higher. If I have an object on a lift and the lift is accelerating downwards, then the normal contact force is lesser. So it changes with n. It is not dependent on weight, but on n. Second point, it is F max. This is really, really important. Why? Let me illustrate this again. If I got a big force F and say F max is equals to 5 Newton, and if I drag the object with 1 Newton, the frictional force is not going to be 5 Newton, it's going to be 1 Newton. Alright? And if I increase it to 5 Newton, it will still be 5 Newton. And at the moment when I increase this any further, this will stay at 5 Newton. But of course, when it starts to move, the 5 Newton will actually decrease to a lower value because it will become mu k, which is lesser than mu s. So you have to be very mindful that the F equals to mu n gives you the maximum frictional force, not the frictional force at all times. If my frictional force is, if the force I apply is lesser than the maximum frictional force, then the frictional force will be lesser. It's not equals to the maximum frictional force. So be very mindful. F max, the max idea about the max, and that it is n, not w. Next one, the idea of Newton's second law. Now for Newton's second law, you have to be very aware that it is F equals to dp dt, and it is equals to ma if and only if the mass is constant. You have to know the condition. Now for F equals to ma, you need to know how to draw free body diagram. Say for example, if I have an object on a ramp and I apply a force F, there will be frictional force here, there will be normal contact force, there will be weight. So this is a free body diagram on the small block. Whereas on the ramp, it's going to be interesting. The force on the ramp is N, not the weight of the block. And the frictional force on the block is downwards, so the frictional force on the ramp is upwards. And there's the weight of the ramp, and there's a second normal contact force by the ground on the ramp. Okay, so this is the free body diagram for any objects, and usually you have to apply F equals to ma to solve the questions. I've gone through a lot of examples with you in class, so refer to those examples, how you use F equals to ma on a situation. But I wanted to emphasize the importance of the free body diagram, because without the free body diagram, you don't know how the forces are related. And that's the fundamentals for circular motion for other systems. The next thing I want to go to is the idea of impulse. That if you take F dt integral, it is actually the change in momentum. So if you take the force multiplied by time, it will give you the change in momentum. This is actually quite easy if you have forces which are linear. So if I apply a force that is this way, the force multiplied by the time is equals to mv minus mu. Now it becomes more difficult if I have an object this way and I apply a force this way. Now what you have to do is to take the initial momentum, okay, starting from the idea that the change in momentum is equals to F times time. Usually the F is given, the time is given, the M is given, the U is given, you want to find V. So how do you apply this? Remember that it is a vector quantity, so MV is equals to MU plus FT. These are both vectors. So you take this vector plus this vector, then this will give you the final vector, which is MV vector. So all you need to do then is to take that vector divided by the mass, and you get the final velocity with the direction given over here. Okay, so this is the change in momentum, impulse, and Newton's second law in a nutshell. You also have to know, for the last part of this topic is the collisions. You need to know that conservation of momentum is states that the total momentum of a system is conserved if no net external force acts on it. Very important part, no net external force. Must remember this. There are three collisions: elastic, completely inelastic, and completely inelastic. How do you know it's completely inelastic? They get stuck together. How do you know it's elastic or inelastic? Difficult to tell. But elastic collision, you know that it will obey this equation. In elastic collision, you have to check the Ke before and after and see whether the Ke before and after are the same. If it is not the same, it will be inelastic. Alright? And I think something is quite obvious. There is an obvious consequence of this. Probably I just state this. If you got A and B hitting each other, you need to know that the change in momentum of A is equals to negative change in momentum of B. This is the consequence of this. But you just have to know that because of this is true. But sometimes questions may require you to know this, that the change in momentum of A is equals to the change in momentum of B, but in opposite direction. Okay, so this is basically it for topic 2.3. Now topic 2.4 is work energy power. Very important idea about work, very important idea, is this notion of work done equals to force times displacement. This is not the most important part. The most important part is this, in the direction of the force. This is the critical part where tricks can be done. So let me show you an example. So if I apply 80 Newton force over here and the mass over here is say 10 kg and this is 30 degrees over a distance of 6 meters, I'll probably increase it to 120 newtons. So if I ask you to find the work done by the force, pulling force, and the gain in GPE, this will be 120 times 6, whereas this one will be 10 times 10 times 6 times sine 30. This will be 720 joules. This will be 300 joules. Why is it that I take 120 times 6 over here, whereas this one I take this? Because if you take a look at this force is in this direction, that's why you take this distance. It must be in the same direction as the force. Whereas mg over here is vertically downwards, so we have to take that vertical height. That's why it is 6 times sine 30. It is very important for you to realize this, so you understand why is it that we substitute certain distances and not the other one. Alright? So, very important idea. mgh half mv square, I don't think I need to go into the details of that, but you need to know this idea that force times displacement is the work done. In the direction of force is the work done. Cool? So, this is basically it. The one more thing about work done is force, displacement. If you've got a graph like this, you need to know that the area under here is the work done. Be very careful that this is meters. If I were to set a question, I'll definitely give it in centimeters and kilonewtons. So be very careful about this. And the work done must be equal to the change in energy of the body. So if I do some work, it must increase the Ke, GPE, or both. Or probably even reduce depending on the direction of the force. Like frictional force. Work done by frictional force will be to reduce the energy. Cool. So that's basically it for topic 2. I know I'm making it sound too easy, but this is basically the more important points here and there. I can't tell you exactly what the question is, obviously, but I can tell you that it will not be too far away from whatever I mentioned over here. Now, with this, let's move on to 3.2. So, topic 3. Topic 3 is I think, in my opinion, is one of the easiest to handle. Well, compared to topic 4 and topic 9, everything is easy. I'm sure. So, topic 3.1 is on ideal gas. For those of you who do chemistry, it will be really simple. PV equals to nRT, PV equals to nKT. So you need to know the conditions for ideal gas. You need to know the assumptions for ideal gas. That there is the volume of the molecules is negligible compared to the volume of the container. And the second one is that the intermolecular forces of attraction is negligible compared to the Ke. So the way to achieve this is to have high temperature and low pressure. So you will achieve the assumptions. Now you have to also know how to use this too. So say for example, if I were to have a movable piston and I heat up the gas so the movable piston moves up. So you need to know how to find the new volume if the piston can move. So how do you handle this kind of question? You look at PV equals to nRT. Tell yourself which is the quantity that's constant. N is constant, R is constant. In this case, P is constant because the piston will move until the pressure are the same. So the way to go about this is to put this on one side and put the rest on the other side. So then you know that if this is constant, then this must be constant, and hence this must be true. So the key over here in solving this kind of question is to find out which of the quantities in the gas container is constant, and then shift all the constants on one side, shift the variables on the other side, and then this initial equals to this final. Okay? Now the next one is 3.2. 3.2 is really quite O-level stuff. You need to know your specific capacity, your heat capacity, and your latent heat of fusion. You need to know how to explain why is it that temperature stays constant when you are melting or vaporizing a substance. You also need to know how to handle situation, explain what's the effect of heat loss on the calculated quantity. So say for example, if I were to supply a Q amount of energy, I measure a change in temperature, there's a mass M, and I calculate the C to be Q upon M delta theta. Now is this a higher value or lower value than the actual value? So what actually happened is that out of the Q, some portion is lost, Q naught is lost. So therefore, you have the Q minus Q naught to be the actual one, to be equals to C. So this is the correct one. This is the correct one. This is the one where you have not accounted for heat loss. So I think this is quite clear that this is going to be smaller. So the actual value is going to be smaller, the calculated value is going to be higher. Alright, so this is how you find out what's the effect of the heat loss on the calculated value. And that's it for topic 2 and topic 3. And I hope that this will help you understand some of the more important points that you have to take note of in topic 2 or topic 3 revision. Thank you, and stay tuned. I will go through topic 4 very soon.